packing efficiency in crystals. The particles such as atoms, ions or molecules, they are closely packed in several different ways. In each type of close packing, there is always some vacant space in between the constituent particles in the form of voids. We know there are two types of voids in packing, tetrahedral voids and octahedral voids. Thus, in the packing, a part of total available space is occupied by constituent particles. The percentage of the total space filled by the particle is called packing efficiency. Different type of packing arrangements have different packing efficiencies. Let us calculate different packing efficiencies in different arrangements. Packing efficiency in simple cubic lattice. Let's start. Simple cubic lattice, the 8 atoms or spheres are located on the corners of the cube. The particles touch each other along the edges. Number of atoms per unit shell in simple cube is 1, that is the rank. Each atom is considered as one sphere. Volume of one atom or one sphere is equal to 4 by 3 pi r cube. Edge length is a and small r is the radius of one atom or the sphere. Now, edge length a is equal to 2r. The volume of cubic unit cell is equal to a cube. Now it is 2r whole cube, that is 8r cube. Packing efficiency is equal to volume of one atom divided by volume of cubic unit cell multiply by 100%. That is your packing efficiency in percentage. Now volume of one atom is 4 by 3 pi r cube and the volume of the unit shell is 8 r cube. Now it is equal to pi by 6 into 100 and your answer will be 52.36% or 52.4% approximately. Now the vacant space available in simple cubic unit shell, that is equal to 100 minus 52.4% is equal to 47.6%. Packing efficiency in HCP and CCP structures. Let us calculate packing efficiency in CCP structures. Cubic close packing is same as face centered packing. In this type of arrangements, the particles are touching one another along the face diagonally. Let the edge length of the unit shell be A, radius of each sphere be R, and the face diagonal be B. Now AC is equal to B, which is equal to 4R. Now let us calculate edge length A by applying Pythagoras theorem. In triangle ABC, AC square is equal to BC square plus AB square. B square is equal to A square plus A square. Now B square is equal to 2A square. Therefore B is equal to square root 2A, which is equal to 4R. Now A is equal to 4R divided by square root 2, which is equal to 2 square root 2 r. Volume of the cubic unit shell is equal to a cube, which is equal to 2 square root 2 r whole cube. That each unit shell in F.C.C and cubic unit structure, the number of sphere is 4. Volume of the 4 sphere is equal to 4 into 4 by 3 pi r cube, which is equal to 16 by 3 pi r cube. Now, the packing efficiency is equal to volume occupied by 4 sphere in the unit shell multiply by 100, and that is divided by total volume of the unit shell. Now, packing efficiency is equal to 16 by 3 pi r cube divided by 2 square root 2 r whole cube, and that is whole multiply by 100. Packing efficiency is equal to 16 by 3 pi r cube divided by 16 square root 2 r cube. Now that is equal to 74%. Now packing efficiency is 74% in HCP or CCP. Efficiency of packing in body cubic structures. In body structure unit shell, there is a particle at the center of the body, and as well as 8 atoms are present at the corner, one on each corner. Clearly seen here, atom at the center will be in touch with the other two atoms diagonally arranged. Let A be the edge length of the cube and R is the radius of the sphere which are diagonally. Body diagonal AF is equal to C and face diagonal FD is equal to B. Now AF is equal to C is equal to 4R. Now let us calculate the body diagonal C and face diagonal B. Using these values, we can calculate A. Consider the triangle EFD. By using Pythagoras theorem, FD square is equal to EF square plus ED square. Now B square is equal to A square plus A square. B square now is equal to 2A square. The value of B is equal to square root 2A. Now in triangle AFD, AF square is equal to AD square plus FD square. Value of AF square is equal to CS square. Now CS square is equal to A square plus B square. Now we will put the value of B square, that is equal to 2A square, and the value of C square is equal to now 3A square. Now C is equal to square root 3A. C is a body diagonal. C is equal to root 3A. We will put the value of root 3A is equal to 4R. From here A is equal to 4R divided by root 3. Now the volume of the unit shell we know, that is a cube, which is equal to 4R divided by square root 3 का whole cube. In body-centered cubic unit shell, the number of particles per unit shell is 2 atom, that is the rank. Each atom is considered as one sphere. Now the volume of 2 atoms is equal to 2 multiply 4 by 3 pi r cube, which is equal to 8 by 3 pi r cube. Now the packing efficiency in B.C.C is equal to volume occupied by 2 sphere in the unit shell multiplied by 100 and divided by total volume of the unit shell. Now, packing efficiency is equal to 8 by 3 pi r cube multiplied by 100 divided by 64 r cube divided by root 3 multiplied by 3, and the packing efficiency now is equal to 68%. In body-centered cubic unit shell, the packing efficiency is 60%, and 60% of the unit cell is occupied by the atom. Now the free space is 32.
Thank you, students. I hope you like the video and you are able to understand what is the concept of packaging and how we will calculate the packaging in three-dimensional structures like B.C.C, H.C.P, C.C.P and the simple cubic unit shells. And these packing efficiency are just nothing. We already explained these are the concept how the atoms are packed in a structure, and you can also calculate the empty space which are known as voids in a structure. I hope you like the video, and in your next section we will move forward and we will see the imperfection in the solids, and what are the calculation we can do and what are the numericals we can include in that chapter. Thank you so much. Hope you all are well.